Hi, my name is Alex Jang,
And I'm Matt Simonelli.
and thanks for checking out our video on the self-regulated pump research we are conducting.
Okay, so before we begin talking about what we've accomplished throughout our research, we should explain some background information related to our project. The Starling resistor is a device that restricts fluid flow in a very special way. It consists of a static pressurized chamber, typically air, and an elastic tube with a pressure difference across it. This allows for the inner tube to be stretched and deformed under fluid pressure as it acts upon it. Currently, these fluid resistors are found naturally in the heart and lungs, but not much is known about their purpose or effects they have on fluid flow. Studies shown that in biology they help regulate the blood pressure, but not much is known about the physical phenomenon. An article written by Roger Wang and his colleagues showed that the inner tube deformation can achieve oscillations according to certain mathematical simulations. Some oscillation patterns are shown on the left here on this slide, and the experiment setup is shown on the right. We will be attempting to recreate these oscillations on a smaller scale using air as our external pressure. These graphs show that the Starling resistor can cause constant flow output for a range of input pressures. The graph on the left is a target graph, and the graph on the right is actual data from a study gathered at MIT. Controlling flow rate for variable pressure inputs is a complex task. A fluid power system would typically require a sensor and an adjustable valve in order to control flow rate for different pressures. The Starling resistor, however, can achieve constant flow rates for a range of input pressures much cheaper and easier than current technology can.
With the background information established, here is our initial lab setup. For original design, a 2-inch diameter polycarbonate tube was used as the pressure chamber. Polycarbonate was chosen due to its high pressure rating compared to other similar materials like acrylic and ABS. The inner tube was a 1/16-inch diameter soft rubber tube, and to seal the pressure chamber, a large oversized washer and Gorilla Glue epoxy were used. After initially pressurizing the tube, the original prototype had a few design flaws. When sealing the chamber, it took a long time for the epoxy to cure, and the air pressure would leak around 60 psi. The prototype also had trouble retaining its connections with the two-sided barb connectors. The inner tube deformation was achieved around 45 psi, however we hope to achieve a lower deformation pressure. Here is a new and current design for the Starling resistor. Larger double-sided barb connectors were used to accommodate for the larger inner tube diameter. By using larger barb connectors, the air seal was improved as well. The larger inner tube lowered the deformation pressure to around 10 psi compared to the original 45 psi. Zip ties were also used to secure the inner tube connection to the hose barb. With the deformation achieved around 10 psi, the next step was to create a pressure difference across the inner tube. This is the flow diagram we plan to use. This is a closed loop that recycles water. The pump forces water from the bucket and towards the needle valve. Pressure gauges are installed before and after the needle valve to measure the pressure from the pump and the pressure going into the Starling resistor. Through the Starling resistor, flow is regulated and the water is pumped back into the open bucket. Here's the actual test setup. On the left is the specific equipment that was used for this experiment. A 60 psi 4 GPM diaphragm pump, a 100 psi pressure gauge, and a bucket to recycle water.
After setting up our test, we were able to document some successful results. Next is a quick video that shows our test running while the Starling resistor is oscillating. Here are some close-up pictures of the oscillations that occur at the right end of the tube. This can be seen in the next two videos, one of them being the previous tube that was tested, and the next one being a smaller, more compact tube that works the same way. I know our project may have been a bit confusing, so here's a quick recap to emphasize the important parts of our project.
The Starling resistor is an interesting physical system which allows for easy flow rate control. This constant flow rate for variable pressure is shown on the graph to the right. The oscillations of the inner tube are what allows the resistor to output a constant flow rate for different pressures. The Starling resistor will connect to a small pump to create a self-regulated pump, much simpler and cheaper than they are currently made.
During our test, we were able to confirm that once the inner tube deforms due to air pressure, the inner tube will oscillate when a pressure difference is induced across it. Steady oscillations begin when the water input pressure is roughly 5 to 10 psi above the air chamber pressure. This is exactly what has been done at MIT, and we hope it will create a constant flow rate once we measure flow accurately. We were able to get two different length tubes to oscillate, and hope to get even smaller tubes to oscillate and that they will behave in a similar way.
Those are the current results we got. Here is the future outlook for the self-regulated pump. Next, we plan to measure the average flow rate to confirm the Starling resistor is regulating flow. We plan to graph this data against pressure input and hope to see a flat line. Eventually, we would like to move towards lower flow rates, which involve smaller inner tubes. Current research on the Starling resistor is being done at MIT on a larger scale. Some examples include irrigation and sprinklers, which could greatly benefit the farming industry. Future applications of our research would involve the medical and research field. A specific use that is being developed is medical drug delivery system at a much cheaper cost. Once again, this is Alex Jang.
And I'm Matt Simonelli. Thanks for taking the time to listen to our presentation.